Morning, everyone. Don't wash your method. Morning, everyone. Today's music brought to you by Offenbach, interpreting Raymond Lévesque's Quand les hommes vivent d'amour. Raymond Lévesque, who passed away last night. This song is so big that, well, first of all, anybody who speaks French knows that song. Any French artist has sung that song. A lot of French artists have recorded that song. It's a huge song. I will have office hours today after class, noon to 2 as usual. There is some material on WebWork 2 that we have not done. I opened it up nonetheless. Normally, I would have just opened up WebWork 3, which is what we have learned, but experience has taught me that if I open up WebWork 3 and not WebWork 2, then I get inundated with emails asking if this is correct. So that's why I opened up the two WebWorks simultaneously. You have all the knowledge required to do WebWork 3. There is some material yet to come for WebWork 2. Questions? Anybody? How are we doing with partial fraction decomposition? We'll see. We'll see. If we don't cover all of the WebWork 2 material, we'll postpone. Paul is asking which week will the midterm be? I mean, it's already been announced, right? I mean, we have a midterm date already announced. All right. Questions, anyone? Let's continue. Right, I mean, we did some partial fraction decomposition, but didn't really apply to integrals. So let's do that now. The midterm will cover certainly everything we've done so far, and probably 6.1 as well. I'll make an announcement as soon as we have covered everything. All right. Consider this. Well, I mean, Marie, I'm sure you're not alone in not completely understanding partial fraction decomposition. We'll do some more today. It takes a while to wrap your head around the idea. But suppose we had this integral. You see what's happening there? Instead of trying to integrate that immediately, why don't we apply partial fraction decomposition to the integrand? Let's decompose the denominator into a product of irreducible polynomials. And as Zoe mentioned, I mean, and thank you for that, you could have done a trig substitution here. You could have completed the square, made a u substitution followed by a trig sub, and this would have worked as well. But that's a lot of work. That is a lot of work. Instead, if you factor the denominator is easily seen to factor like this. And, well, I mean, first of all, let me point out that the numerator has lesser degree than the denominator, right? Numerator has degree 1, denominator has degree 2. So we're in a situation where we can apply partial fractions immediately. You decompose the denominator into a product of polynomials of degree 1, and you know these to be irreducible. So we search for a polynomial of degree 0 on top. Where a and b are real numbers. If you multiply everything back up, and if you put everything back over common denominator, you get a times x minus 4 plus bx. And now the denominators are equal, so the numerators have to be equal. And we get a times x minus 4 plus b times x is equal to x minus 12. You have options here. You can expand and group and equate the coefficients. Or if you plug in a good value of x, that may be useful as well. And if x is 4, this is completely gone. And you get 4b is equal to minus 8. So b is easily seen to be minus 2. And if x is 0, you get minus 4a, right? If x is 0, this is gone. And minus 4a should be minus 12. So a is easily seen to be 3. Somebody was asking if I had passed midterms. I do not. If you want to prepare for the midterm, do all the odd numbered exercises in the book. So what are we saying? We are saying that x minus 12 over x squared minus 4x is actually equal to 3 over x minus 2 over x minus 4. And you see the beauty. Zoe was suggesting that, right? I mean, so we have this. So the integral is going to be the integral of that. Zoe was suggesting completing the square and making a trig substitution, which is perfectly fine, but a lot of work. Here, a bit of algebra transforms this into something trivial, something you can just read off. You know the antiderivative of this. 3 ln x. You know the antiderivative of this. Throw in your arbitrary constant, you're done. So there it is. You exchange a little bit of algebra for an easier integral. How are we doing? Of course, again, let me point out that you can verify that this is correct, right? By putting everything back over a common denominator, and you should end up with that. So you can check your algebra. Right, isn't it? Perfectly balanced. All right. We'll see. We'll see if we get to new material. Who knows? But for sure, this is the last time we're doing partial fractions. All right. So once again, let's decompose the integrand. Using partial fractions. Paul is asking if we need to do long division first. The numerator has degree 1. The denominator, if you multiply that out, would have degree 2. So we're good to go. If the numerator is of equal or higher degree than the denominator, then you have to start with long division. Absolutely. But here we're good to go. And here, luckily for us, the denominator is already factored into a product of irreducible polynomials. So we're really set here. And you see, right? Let's take a step back here. Whatever A and B are going to be, whatever real numbers A and B actually turn out to be, these integrals will be trivial. Right? You could actually evaluate the integrals here regardless of what A and B are. I'm sure you can do that immediately. So again, same denominator, we can equate the numerators. This should be equal to y. Again, you have options. You can expand and equate the coefficients, as you know how to do, or plug in some good values. So if y is 1/2, this whole thing is 0. So you get 9b over 2 is equal to 1/2. So b is easily seen to be 1/9. And if y is -4, you get -9a is -4. So a is easily seen to be 4/9. Absolutely, Marie, thank you. And consequently, this integral is just the integral. A is 4/9, so 4/9. Let me pull it out. 4/9 times 1/y plus 4 plus 1/9, 1/2y minus 1. Right? And a simple u substitution does the trick for each of these. Well, Rima, that's the trick. I mean, that's not always possible, right? It's not always possible to do so, but if it happens, then, I mean, it's very desirable. So, make a u substitution here. Ln of y plus 4. Make a u substitution here. Throw in your arbitrary constant and you're done. Well, whatever answer you get should be exactly equal to this, right? Yeah, derivative. The lawn plays an important role. Absolutely. Thank you, Paul. Paul has realized that the numerator is of equal degree as the denominator, so we have to start with long division. So let's do some long division. And we ask the question, what must we multiply to x squared to get a 3x squared? And of course the answer is 3. And we subtract. This minus this is 0. This minus this is minus 3x. And this minus this is minus 4. The degree of the remainder is less than the degree of the divisor. We're done. Conclusion. What does that mean? That means that this is equal to 3 plus the remainder over the divisor. Now again, you should convince yourselves. Convince yourselves that this is right by putting everything back over a common denominator, and you should get what you started out with. So you see this integral, very easy. Is the video lagging a bit? Seems to be kind of lagging. How's it on your end? Is it all right? It's a bit, yeah. All right. I'll see what's going on there. I mean, Videotron have been having issues, and I am streaming on Videotron there. So, all right. So there it is, right? Now this integral is trivial. So let's concentrate on this one right here. And minus 3x minus 4 over x squared plus 3x plus 2. Let's decompose the denominator here into a product of irreducible polynomials, and this is obviously x plus 1, x plus 2. So this should decompose as a over x plus 1, b over x plus 2. Put everything back over a common denominator. And so we see that the numerators must be equal. Again, you have options there. Rima is asking long division if the degree of the remainder is bigger than the degree of 3. No, not the degree of 3, the degree of the divisor. The degree of the divisor. Right, so if the remainder has degree bigger than or equal to that of the divisor, you keep going. If the degree of the remainder is strictly less than the degree of the divisor, that's when you know you're done. So here we are suggesting to plug in -2. This is going to be 0, and you get negative b is 6 minus 4, which is 2. So b is -2. And if x is -1, this is 0, and we get a is -1. Is that what we have there? So this a is -1, so -1 over x plus 1, and b is -2, so -2 over x plus 2. There it is. And let me bring this down right here. Antiderivative is trivial, so you see again, a little bit of algebra. The integration is trivial. 3x minus ln of x plus 1 minus 2 ln of x plus 2. From 1 to 2, 6 minus ln 2 minus 2 ln 3. No, what is this? 6 minus ln 3 minus 2 ln 4. Subtract, plugging in the 1, so we get -3 plus ln 2 plus 2 ln 3. Let's clean that up. 6 minus 3 is 3. 2 ln 3 minus ln 3 is ln 3. And this minus that is -3 ln 2. But how do you know it's a over 1? Couldn't it be ax plus b over 1? Or ax squared plus bx plus c over 1? Right? I mean, there's some problems there. How are we doing here? Questions? Right, what happened to the -2 ln 4? Anybody? Everybody? Very nice. Thank you, Vincent. -2 ln 4 is the same as -4 ln 2. Yeah. So you've got -4 ln 2 plus ln 2 gives you a -3 ln 2. All right. Consider this. Again, we're going to simplify this using partial fractions. Here's my question to you. How does this decompose according to partial fractions? Marie's asking how far to simplify for the final answer. Simplify completely. That's good enough. That's what I'd be looking for as a final answer. Isn't the bottom already irreducible? Very nice. Very nice observation. This is already irreducible. Correct. So what does the the numerator will be of third degree. I'm not sure what you mean there. The denominator is, of course, a polynomial of degree 4 if we were to expand that. Numerator is of degree 2, so we're ready to go. My question to you is, how does this decompose according to partial fraction decomposition? Ax plus b, right? I mean, x squared plus 2 is irreducible here, right? You know that to be irreducible. So exactly as Zoe suggests, ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 all squared. There it is. Very nice. So I'll give you a moment to put everything back over common denominator, solve for a, b, c, d, but I think it's clear that a is going to be 0, b is going to be equal to 1, c is going to be equal to 1, and d is going to be equal to 0. Take a moment, work that out. No. Smallest common denominator, Sophia, smallest. Your common denominator is going to be x squared plus 1 all squared, the original one. Here, all I'm missing is another x squared plus 1. And here, I've already got the x squared plus 1. And you get an x cubed on top, absolutely. So a has to be 0. Right, so I mean, if we expand everything, this is ax cubed plus bx squared plus ax plus b plus cx plus d. And so now if you equate the numerators, and let's group the powers here. So you get ax cubed plus bx squared, a plus c times x, and b plus d. And that should be equal to x squared plus x plus 1. So now let's equate the coefficients. Coefficient of x cubed on the left is a. Coefficient of x cubed on the right, there is no x cubed. So coefficient is 0. Coefficient of x on the left is b. Coefficient of, x squared. Coefficient of x squared on the right is 1. Coefficient of x on the left is a plus x, a plus c. Coefficient of x on the right is 1. Constant, or coefficient of x to the 0 if you prefer. And coefficient of x to the 0 on the right is 1. So you see A is 0, B is 1. If A is 0, then C has to be 1. And if B is 1, then D has to be 0. Exactly as suggested. How did I know? How did I know without doing anything? Well, you see, partial fraction decomposition is unique. So if you have a partial fraction decomposition, then you have the. We put everything back over a common denominator, the usual. We expand it, and instead of plugging in values of x, which you can, but we have a second approach, right, by equating the coefficients. So here I rewrote everything. I rewrote this expression here by combining the x cubes and the x squares and the x's, a plus c times x, and the constants, b plus d. And now you equate the coefficients. Coefficient of x cubed on the left is a. Coefficient of x cubed on the right, you don't have an x cubed. You have 0 x cubed. Coefficient of x squared on the left is b. Coefficient of x squared on the right is 1. Coefficient of x on the left is a plus c. Coefficient of x on the right is 1. Constant on the left, constant on the right. Did everybody figure out how I knew this answer without doing any work? Right? Partial fraction decomposition is unique. So if you have a partial fraction decomposition, you have the partial fraction decomposition. This is x squared plus 1 plus x. Right? All I did was change these two and then break it up into two fractions. Right? Just break it up into two pieces. So if this is ax plus b and this is cx plus d, a is 0, b is 1, c is 1, d is 0. Susan is asking, when we go back to solving the integral, don't we get another rational function? Indeed you do. Absolutely. You still get another, well, and that's exactly, right? That second fraction, you won't have to decompose it again because it will already be in partial fraction form. And that's where students sometimes mess up. And it's important that you recognize that something is already in partial fraction form. So as Susan is suggesting this is now the same as this. This is easy to integrate. And now some people might want to apply partial fractions to this. So it's important, it's very important that you don't waste 20 minutes working out the partial fraction decomposition for this, because it's already in partial fraction form. You've already done partial fraction decomposition. This is it. This integral, trivial. What about this one? How do we integrate this? So, as Kat suggests, the first one is arc tan x. Thank you. And this one? Trig sub, possibly, but I think there's something easier, and as Dario suggests, u sub is the way to go here. Because you recognize the derivative of x squared plus 1 to be right there. But for the left fraction, the numerator is 2 degrees less, correct? But that's still part of the 1 degree, right? I mean, ax plus b, a could have been 0, right? Remember the partial fraction decomposition, we had the numerator being of lesser degree than the denominator. It doesn't say 1 degree less, it just says less. So if you have a polynomial of degree 2, we search for ax plus b on top, but the a could be 0, as it is here. So this is easily seen to be arc tan x. This is easily seen to be minus 1 over 2 x squared plus 1. Throw in an arbitrary constant, let's call it C1, and we're done. How are we doing? Questions here? Everybody with us? All right. You're looking at this and you're thinking, how do we get the minus sign here? If you do this u substitution, what do you get? This integral becomes 1/2 1 over u squared. And right, this is 1/2 u to the -2, whose antiderivative is, together 1/2 here, u to the -1 over -1. So thank you, ladies. It was suggested that we should do long division, right? Numerator has degree higher than the denominator. So we'll start with long division. Let me put some placeholders here. 0x4, 0x cubed, 0x squared, x and 1. And we ask the question, what must we multiply to x cubed to get an x to the 5? And the answer is an x squared. So x to the 5 plus x squared. And we subtract, this minus this is 0. 0, 0, minus x squared. Bring down the rest. And repeat. Well, actually there's no repeating now. The remainder is of lesser degree than the divisor. We are done. That was painless. So this is equal to x squared plus the remainder over the divisor. We are dividing because we want the numerator to be of lesser degree than the denominator, exactly that, right? Because that's one of the hypotheses of the partial fraction decomposition, that we are starting with a numerator whose degree is strictly less than that of the denominator. All right. So there it is. So this integral, trivial. So now we have to tackle this one. X cubed plus 1 is not irreducible. It's of degree 3. So you know it has to factor into a product of irreducible polynomials. And we see that this has a root. -1 is a root. So x minus -1 or x plus 1 has to be a factor. So let's do some long division. What must we multiply to x to get an x cubed? The answer is x squared. And we subtract, this minus this is 0, this minus that. Bring down the next term and repeat. What must we multiply to x to get an x, a negative x squared? The answer is negative x. So negative x squared minus x. Subtract again. We get an x. Bring down the next term and repeat. What must we multiply to x to get an x? The answer is 1. You get an x plus 1. And when you subtract, you get a remainder of 0. Exactly as expected, and as Haroon has suggested, that is absolutely right. So x cubed plus 1 factors as x plus 1 times x squared minus x plus 1. Now you can check that this is irreducible, as the roots negative b plus or minus square root of b squared minus 4ac all over 2a. You have a square root of a negative number here, so no real roots, and consequently this is irreducible. Let us so let's well, I mean, we now, so I mean, this integral is trivial, so we're focusing in on this, and this is a polynomial of degree 2 divided by a polynomial of degree 3. Polynomial of degree 3 is not irreducible, so we're going to apply partial fraction decomposition to this. In order to do so, we need to know how x cubed plus 1 factors. Now, I don't know how x cubed plus 1 factors, but I can see a root. Negative 1 is a root. So x minus negative 1 or x plus 1 must be a factor. So I'm doing long division to see, to get exactly this, a decomposition into a product of irreducible polynomials. Now I'm going to apply partial fractions to this. And how does this decompose according to partial fractions? Here we have an irreducible of degree 1. So a over x plus 1. Here I've got an irreducible of degree 2. So bx plus 1, c over x squared minus x plus 1. Let's put everything back over the common denominator. Everybody with us here? Have you solved for A, B, and C already? Let's expand all of this. So ax squared minus ax plus a plus bx squared plus cx plus bx plus c, all of this should be equal to negative x squared plus x plus 1. Let's group. We get an a plus b x squared minus a plus b plus c x and a plus c, and all of that is minus x squared plus x plus 1. So let's equate the coefficients. We see that coefficient of x squared on the left, a plus b. Coefficient of x squared on the right is negative 1. Coefficient of x on the left, coefficient of x on the right, constant on the left, constant on the right. This whole thing is equal to that. I'm just equating the numerators. And now This is again this business, so this whole thing is equal to that. Right? It's just equating the numerators. So this big expression is equal to this. This big expression is equal to that. Right? I mean, it's the same thing. All I'm doing is I'm grouping. Everybody with us? 3 equations, 3 unknowns. So solve using matrices or otherwise. Here, B is equal to minus 1 minus A. Here, C is equal to 1 minus A. And if you plug both of these back into this, you get minus A. B is minus 1 minus A. And C is 1 minus A. This whole thing should be equal to 1. These cancel out. And we get minus 3A is equal to 1. So A is minus 1/3. If A is minus 1/3, then B is minus 2/3. And C is 4/3. So what are we saying? This is now, we said A over x plus 1 plus bx plus c over x squared minus x plus 1. All right. How are we doing? Understand that we have not done a single integral yet, right? It's certainly fine to use matrices, absolutely. Well, if you think that's a lot, we haven't finished. We have not finished this question yet. Easy. Easy. What about this one? So let's concentrate on this integral. Very nice. Very nice, very nice. Turn that one into, sure, I mean a few things. First, why don't we take out a negative 1/3? Let's take out a negative 1/3, leaving us with 2x minus 4. Is that correct? Right? And it'll be easier to see. What are we thinking? We're thinking, why not a u substitution? Why not u equals x squared minus x plus 1? In that case, du would be what? Du would be 2x minus 1. The problem is I don't have a 2x minus 1. I have a 2x minus 4. We could take out the 2 as well. I left it in because I saw what was going to happen, right? The derivative of the denominator would be 2x and some other stuff. So that's why I wanted to leave the 2 in. But you see the issue. You cannot make a u substitution because you don't have 2x minus 1. Instead, you have 2x minus 4. But we can remedy that, right, by rewriting this 2x minus 4 as 2x minus 1 minus 3. Very nice. Very nice. So that this part right here will call for this u substitution. Right? So if you break that up into 2x minus 1 over x squared minus x plus 1, then this part will call for a u substitution, and that's all well and good. And that will just leave you with a minus 3 times minus 1/3, so a plus so now this integral is easy. So that integral is easy, that integral is easy, that integral is easy, because it's just a u substitution. So now we're just left with this last integral. So all we have, right, a little bit of algebra, some long division, some partial fraction decomposition, 3 easy integrals, and then this last one to finish up. How do we integrate that? And Haroon, I believe, had given us the answer originally, completing the square. If you complete the square here, this is x squared minus x plus a quarter plus 3/4. And this breaks up as x minus 1/2 all squared. Well, you do have 3 days, right? How did we get to the top right? I just split this up into 2 pieces. This over that and that over that. And the 3 you can bring outside. Exactly. Luckily for us here, this is an easy integral, but you can imagine you can imagine in a more complicated setting where you would be forced to do trig sub. Omar, are you asking the number of questions? I have not written it yet. So far, I have 2 questions. So there it is. You know what to do, right? We're going to make a u substitution. V equals x minus 1/2. So that dv is dx. Why isn't it 1 over u? Well, it's not 1 over u because the derivative is 2x minus 1, and we had that in this first part. The exam is the same for all sections, right? If you try u substitution, you don't have this 2x minus 1 in this integral here. So that u substitution does not work. Integration by parts, I mean, I'll invite you to do it. Not going to work. Not going to work either. All right. So making this v substitution brings it to 1 over v squared plus 3/4. Then you can either, you have options. You have options. I think the easiest way to see it would be to make a trig sub. V is √3 over 2 tangent. So that dv is √3 over 2 secant squared. And that integral becomes √3 over 2 secant squared over 3 over 4 tangent squared plus 3 over 4. And if you factor out the 3 over 4, you get tangent squared plus 1, which is secant squared, which is going to cancel out with this one. So √3 over 2 over 3 over 4, secant squared over tangent squared plus 1. And these just cancel out, right? Because tangent squared plus 1 is secant squared. So this is 2 over √3 theta and 2 over √3 theta is 2v over √3 is tangent theta. So theta is arctan of 2v over 3. So can we put everything together? Where we took v to be square root of 3 over 2. I mean, this has the form. This has the form x squared plus a squared. So So you know that this calls for a tangent substitution. Here, A is root 3 over 2. Where is the top left corner coming from? This was remnants from earlier. I've left it there because now I want to put everything together to give you the answer, right? So what are we saying? Right, this part is really this last integral right here. So what are we saying? X squared, 1/3 over x plus 1. This is 2x minus 1 over x squared minus x plus 1. And then you have this last thing. Two v over root 3, thank you. This should be a root 3. Absolutely. Thank you, Shinshen. So let's give the final answer then. Antiderivative, 1/3 x cubed. Antiderivative, a simple u substitution does the trick. Ln of x plus 1. Antiderivative of this, right? Because the numerator is the derivative of the denominator. I'll give it to you now. This is easily seen to be and this integral, which is what we did here, all the way to there, 2 over root 3. Arctan of 2v, which is x minus 1/2. So 2v is 2x minus 1 over root 3. Throw in your arbitrary constant, and we're done. I don't think that's going to be costly at all. If you forget the plus c, let's not forget it, but there it is. Oh, we still have a good 15 minutes. We didn't do anything new today. How are we doing? Now, of course, you can verify that this is the right answer, right? By taking the derivative, simplifying, make sure that you get what we started out with. Paul is questioning the integral on the bottom. We made a trig substitution, and tangent squared plus 1 is secant squared, so these cancel out, and you're just left with the integral of a constant. You're left with the integral of 2 over root 3, right? This simplifies to 2 over root 3, so the antiderivative is 2 over root 3 theta, and theta is the arctan of 2v over root 3. It came from the integral, Rima. This is 2 over root 3. and this is just 1. So when you integrate, Sophia, maybe I had originally written 2v over 3 here. That was incorrect. I was missing a square root, right? Because theta is arctan of 2v over root 3. That was my mistake. I'd forgotten the square root, so maybe you copied down my mistake, but we changed it. Junshan pointed that out. All right. Let's try one more. Well, I mean, look, what's important here, it's not really necessary to distinguish between the C's. I do it for completeness, but shouldn't we have put it in terms of X? This thing right here, absolutely. Absolutely, that's why I did it here. I did it here to save us a bit of room, but absolutely. Absolutely, right? The original integral was in terms of X. We should write it in terms of X. I did it as the last step there. But yeah. Right, and I was going to say the important thing is to know what to do at every step of the way. That's what's important here. You started out with a rational function. Numerator had higher degree than the denominator, so long division. Then decompose the denominator into partial fractions. Then you still have a quadratic in the denominator. Complete the square, make a trig sum. It's all good. These are all techniques you're comfortable with. Let's consider this. And Haroon has suggested a U substitution. U equals cube root of X. Let's try that. Seems reasonable enough. I mean, there isn't much else we could really do. So let's do it, see what happens. Then du, this is really x to the 1/3. So du is 1/3 x to the negative 2/3. Or if we bring everything to the other side, 3 x to the 2/3 du is dx. But of course you don't want u's and x's in the same integral. But x to the 1/3 is u. So this is really 3u squared. So this thing, this integrand is 1 over 1 plus u. The dx is 3u squared du. And might as well change the limits while we're here. When x is 0, u is 0. And when x is 1, u is 1 as well. And now it's trivial, right? This is really the integral 3u squared over 1 plus u. I mean, mean, the denominator is already irreducible. This has degree 2. So maybe you want to do some long division. Is the 1/3 supposed to be negative? I don't think it is, right? I mean, it's positive 1/3. So the derivative, you bring the 1/3 down. Let's do some long division. And we asked the question, what must we multiply to u to get a 3u squared? The answer is 3u. And we subtract this minus this is 0, this minus this is a minus 3u. Bring down the next term and repeat. What must we multiply to u to get a minus 3u? The answer is minus 3. And subtract, this minus this is 0, this minus this is 3. And now the remainder has degree 0, which is strictly less than the divisor, which has degree 1. So the integral, we had 3u squared over u plus 1. I mean, I should point out that u plus 1 is irreducible, right? But regardless, long division, this is 3u minus 3 plus remainder over divisor. And once again, you can verify your answer, right, by putting everything back over common denominator. But now the integration is trivial. 3 over 2u squared minus 3u plus 3 ln of u plus 1. When u is 0, that's 0, that's 0. Ln of 1 is 0. Everything is 0. Beautiful. And there it is. Questions? How are we doing? We've been doing stuff from page 515. Let me bring your attention to the next section, page 522. Well, we had made a u substitution, and we had actually changed the limits. So there's no need to rewrite everything in terms of x. Maria is asking why we did long division, because we looked at this and we said we have a rational function here, one polynomial over another, where the degree of the numerator is larger than the degree of the denominator. So we start by long division. A lot of people are asking, shouldn't we change back to x first? I claim that when we did the u substitution, we actually changed the limits to u. It turns out in this particular case that they are the same. So that's very coincidental here, but they are the same. So we can just plug in. Rima's asking where We can review trig functions like arctan and secant. In the book, I think it's Appendix D. Appendix D will give you a lot of trig stuff. And for the inverse trig functions, have a look in the book in the section on implicit differentiation. This is where the book introduces a lot of the inverse trig functions. I mean, we are out of time, so we're not going to do anything today. We will learn volumes at some point. But I mean, starting on Thursday, we're going to do applications. We're going to do some applications starting Thursday. What I wanted to bring your attention to, that these are all taken from page 515. 515, section on partial fraction decomposition. But I want to bring your attention to the next section, page 522, where these are now just a bunch of questions. A bunch of integrals, and you don't know what technique to use, right? Because I mean, what have we seen? Use substitution, integration by parts, trig sub, partial fractions. So, you know, I mean, if you're doing questions from one section, you kind of have an idea of how to start. Here, the questions are all jumbled up. You've got a bunch of integrals. You don't know which technique to use, which is a very nice way to study for the midterm, right? You won't know what technique to use. So there it is. There are no implicit, well, not in our class. There are no implicit antiderivatives in our class. You kind of do that in a course on ODEs or in Cal 3. All right. Thank you all for coming, guys. On Thursday, we're going to start applications, starting with the area between two functions, and we'll take it from there. How many calculuses are there? I mean, it's going to depend on which university you go to. Here we have 4. Some other universities have different names for some courses, but I mean, here Cal 1, 2, 3, and then advanced calculus. It's all part of the calculus stream. And then, of course, if you're very interested, then you can start asking, what about proofs? And then you have courses like analysis, where you prove all the results of calculus. I am referring to the, I want to say, 9th edition. But, I mean, let's just say that it's in the section following partial fraction decomposition. All right. Thank you all for coming, folks. I will see you on Thursday. You guys have a good one.